Imagine standing on the rocky surface of an alien moon. You look up at the evening sky, and instead of a single sun setting, you see a massive gas giant illuminated by two distinct blazing stars. This exact planetary system actually exists. It sits 22,800 light-years away, deep in our galaxy. At the center of that distant system is a massive planet. Depending on how astronomers measure, it is anywhere from the size of Saturn to 7 times the mass of Jupiter, the largest planet in our own solar neighborhood. Locating a planet like this, caught in the gravitational crossfire of two competing stars, is notoriously difficult. Because of this, twin star systems remain a massive blind spot in our map of the galaxy. Over the last few decades, astronomers have officially confirmed the existence of more than 6,100 planets outside our solar system. This animation shows how we found almost all of them, the transit method. We point a telescope at a star and wait for a dark circle, a planet, to cross in front of it, causing a tiny, measurable dip in the starlight. But that method has a severe limitation. If a planet's orbit is too wide, it will never pass between its host star and our telescopes to cast a detectable shadow. Add a second star to the mix, and the problem gets worse. Binary stars engage in a wild gravitational tug-of-war, creating orbital paths so erratic that waiting for a neat, predictable transit is practically useless. If we only look for the shadows planets cast, we miss these complex environments entirely. We needed a completely different way to look at the universe. The solution to observing these chaotic systems is a technique called gravitational microlensing. This observational method is a direct, practical application of Albert Einstein's theory of general relativity. As a massive object, like a star, drifts through space, its immense weight literally bends the fabric of space-time around it, creating a deep gravitational well. When light from a more distant background star passes through that warped region, it doesn't get blocked. The gravity acts as a cosmic magnifying glass, amplifying the background starlight and making it temporarily much brighter to our telescopes. Catching this effect requires perfect temporary alignment. Earth, the drifting lens star in the middle, and the background star all have to line up exactly. If a planet is orbiting that middle lens star, its own gravity adds a tiny extra distortion to the magnified light. Microlensing allows us to detect invisible worlds by how their mass bends light, rather than by the shadow they cast. In 2016, a massive international team of researchers caught one of these precise alignments, an event they named KMT 2016 BLG 1337L. The magnified light initially revealed a binary system made of two M-dwarfs. An M-dwarf is a type of star that is significantly smaller and cooler than our own sun. As the researchers analyzed the brightness curve, they found an unexpected glitch. The light spiked in a way that the gravity of just two stars couldn't explain. To solve the math, astronomers applied a 3L1S model, meaning 3 lenses and 1 source. They mathematically introduced a third gravitational body into the system to account for the glitch. This diagram illustrates the first viable solution they found. It shows a Saturn-mass planet making a wide orbit at 4 astronomical units from its host star. An astronomical unit is the distance between Earth and our Sun. The data also supported a second viable model. In this scenario, the planet is a massive gas giant, 7 times heavier than Jupiter, orbiting much closer at a tight 1.5 astronomical units. While the exact mass and distance are still ambiguous, the math is definitive on one crucial point. A giant planet is hiding in that system. Finding any planet in this environment proves they can form and survive the intense, competing gravitational forces of two stars, forces that models often suggest should tear a planetary body apart. This discovery builds on previous microlensing findings, specifically a Saturn-sized world confirmed in 2016, known as OGLE 2007 BLG 349L. This schematic shows how the OGLE planet survives. It orbits both stars at once in a massive, wide loop. But shifting to the KMT system, we see a different survival strategy. This planet tightly orbits just one star, completely unbothered by the second distant sun. This expands our understanding of planetary evolution. It demonstrates that worlds do not need a solitary, neatly organized solar system like our own to form and stabilize. It also highlights the value of the microlensing method. It allows astronomers to target the hardest to reach, most dynamically complex corners of the galaxy, where standard observation techniques fail. By utilizing the universe's own gravity as a lens, we are mapping impossible, chaotic worlds once thought to exist only in science fiction.